Okay, let's get started. Thanks everyone for coming. So this is a workshop on recent directions in machine learning, and it's organized by Alexander Madri, Arvind and Vijay Raghavan, and Emmy. So the original charter for this workshop came from Alexander and the talk's program chair, Nishith Bishnoi, and it was to highlight some directions in machine learning that may be of interest to a TCS audience, but that are maybe not so well represented in Fox and Stock. So we assembled a cast of speakers, several excellent speakers for this program today and tomorrow, and I'm really looking forward to their talks and hope you are too. So without further ado, let me introduce the first speaker. So Cindy Rush got her PhD in statistics from Yale in 2016, after which she joined Columbia, where she's now Howard Levine Assistant Professor of Statistics. Cindy works on high-dimensional statistics and machine learning and drawing on techniques from information theory, statistical physics, and applied probability. And today she'll tell us about exact high-dimensional asymptotics for statistical estimation via approximate message passing.
Okay, thanks Daniel for the intro, and thanks to the organizers for the invitation. It's nice to be here. So as Daniel mentioned, okay, I'm going to talk a little bit about AMP. So my plan is to kind of give like an overview of its uses. And I hope that I kind of catered the talk a little bit to the TCS audience. So with that being said, I'll go ahead and get started. And I'll mention that this is loosely based on some work with collaborators over at Cambridge. Together, we wrote sort of a survey paper on AMP that's meant to sort of introduce some of the ideas to statisticians. So if you like the talk, check out the paper. Okay, so to get started, a little intro on approximate message passing. So approximate message passing, or what I'll call AMP, is a class of fast iterative algorithms that have many uses. And one of them is for establishing computational limits of statistical estimation problems through exact asymptotics. And so this is kind of what we're going to talk about today. And these techniques have been used in many fields over the last about 10, 15 years. So it kind of got started in studying like just the sort of basic sparse linear regression problem, so kind of in the compressed sensing literature. But since then, it's been used in more generalized linear models. So examples are like phase retrieval or logistic regression. It's been used for low rank matrix estimation, and also for applications in communications. And some recent work studies AMP on neural networks and for deep learning and these sorts of things. So there are kind of two nice features, I think, that make AMP particularly attractive, especially to statisticians or folks who want to analyze problems. So the first is that the algorithm easily incorporates prior information on the signal. So, if your signal is sparse, this is, an assumption we like to make, then it's easy to incorporate this knowledge into the algorithm itself. And kind of the other cool thing about the algorithm is that it comes with precise asymptotic performance guarantees. So we sort of have an understanding of the statistical properties at every iteration of the algorithm. And this is, these asymptotic performance guarantees, which I'll, talk about through the rest of the talk, the same asymptotic regime. It's going to be this large system limit where we're thinking about the number of samples, which I'm calling N, and then the dimension of the problem, which I'll call P. These guys are going to grow together at some fixed constant ratio that I'll call delta. And so there are kind of two uses of AMP that I will highlight today. So the first is that we can kind of pass these precise guarantees for the algorithm itself onto statistical estimators. So it gives us a way of analyzing properties of statistical estimators. And so we'll look at two examples of this. One is the basic example of just, the Lasso estimator for sparse linear regression. And then the second example is a more modern example that looks at the L1 interpolator for the linear model. Another use of AMP that is I think very cool is that it helps us to understand statistical computational gaps. So, in many problems, we're starting to see this phenomenon where, the information theoretic limits of the problem are at one level, but all of our fast algorithms seem to fail at, a different level. And so AMP can be used to help understand these sorts of problems. So I'll also look at an example that kind of highlights this aspect of AMP. So the outline, as I mentioned, so two examples of how we can use AMP to analyze statistical estimators, one sparse linear regression with the Lasso, and then a recent work by Yuting Wei and her student on multiple descent for minimum L1 interpolators. And then we'll talk a little bit about an AMP theory application that gives lower bounds on estimation error for first order methods, and it'll demonstrate some optimality properties of AMP. And then at the end, I'll present sort of a general recipe for analyzing estimators with AMP. So specifically for statistical estimators that are found as solutions to convex programs. And the paper that I wrote with my co-authors, we try to give a sort of step-by-step guide about how to apply AMP to your problem of interest, and we'll go through that. Okay, so let's talk about the first example, which is sparse linear regression with the Lasso. So the basic high-dimensional linear regression model is the following. This is something we've probably all seen and we know and love, but the idea is I have some output Y. This is kind of my data. It's a lengthened vector. And I believe that it was generated as linear measurements on some unknown signal vector beta. And those linear measurements are viewed in noise. So my noise vector I'm labeling as Z, and I think of the variance of the noise as being sigma squared. And throughout the talk, I'm going to assume that my random design matrix has IID Gaussian entries. So the X in my slides that construct these linear measurements are always going to be IID Gaussian. I'll also mention that in the talk, I'm going to think about the vector beta as itself being randomly generated. So I'm going to think that there's a prior distribution on my vector beta. So in particular, I'll think of the elements of beta as being IID according to some distribution P beta. So if you want, if you're believing that your vector beta is sparse, perhaps this prior distribution could be like a Bernoulli Gaussian that puts a large mass on zero and then, a smaller mass on some other non-zero elements. And we'll also talk about the linear sparsity regime throughout. So the probability that an element of this signal of interest, this target of interest, is non-zero, stays fixed as the problem size grows. Okay, so if we want to recover this vector beta from our output Y, and also knowledge of this measurement matrix X, one way to do it, a really common way to do it, is to solve the Lasso, which constructs an estimator as a minimization over two terms. The first is a data fit term that's just the sum of the squared residuals, and then the second is a penalization term based on the L1 norm. And so what the example I want to give today is how AMP can be used to actually analyze properties of the Lasso itself. So when we think about, we want to answer questions like, how well is this beta hat actually estimating the true sort of data generating beta, right? And so we're going to use AMP to do this. So I'll just mention that, the literature on high dimensional estimation provide some analysis of this problem that's not through AMP, right? So you can get upper bounds on prediction and estimation error under various conditions on this matrix X, like restricted isometry or other compatibility conditions. But AMP kind of offers complementary guarantees in the sense that it provides exact formula, so exact characterizations for things like the asymptotic risk or the asymptotic sort of loss between beta hat and beta. And so we'll see how this works. Okay, so I'm going to introduce the AMP algorithm that's used to find this lasso estimator. And to do that, I'm going to sort of motivate the form of the AMP by first considering the standard way that one might solve the lasso, which is the proximal gradient descent method, right? Or for the lasso specifically, it's often referred to as iterative soft thresholding. Right, so iterative soft thresholding looks like the following. At each iteration, we calculate a residual term, and then we update our estimate of, the lasso minimizer using the soft thresholding function acting on that residual. So R hat will always be my residual, beta hat will always be the term that's estimating the signal. In iterative soft thresholding, we have a deterministic step size, which I'm calling eta, and then this ST function is just my soft thresholding function, right? And all throughout the talk, if I define a function, from R to R and it's applied to a vector, I mean to apply it component-wise. So the AMP algorithm looks like the following. It's very similar. So for each iteration, we also construct a residual term and an updated estimate. We also use the soft thresholding function, but there's kind of two differences. The first is that instead of using a deterministic step size, we use a deterministic sort of threshold that changes with the iteration. And then the residual term also has a sort of additional piece there. And in this notation, this L0 norm just counts the numbers of the number of non-zeros in the vector itself. So, okay, when we compare these side by side, right, these are the two differences, the way that the threshold changes, and then also this additional term in the residual. And so this additional term in the residual is some sort of memory term. It's often called an Onsager correction term because, its presence was sort of motivated by some ideas in statistical physics. And so this is kind of the crucial piece of the AMP algorithm because it's what actually ensures that the empirical distribution of the iterates can be characterized exactly in the way we want. And so here's precisely kind of what I mean, or well, we'll see more precisely on the in what follows what I mean. But here's what I'm trying to say when I say we can say something about the empirical distribution of the iterates. So what I mean is that when our problem size is large, so when our samples are large, our dimension is large, then the entries of this estimate at each iteration k in our AMP algorithm have approximately the same empirical distribution as those of a term that we have a pretty good handle on. So this term is going to be the soft thresholding function that acts on a vector that's constructed as the signal itself plus independent Gaussian noise, where the variance of that noise is something I know, right? So now we have kind of just a denoising problem, right? We have the signal viewed in Gaussian noise. And what we can show also is that this variance is going to be in nice situations decreasing as the algorithm iterates. So in general, the sort of the way that we describe this noise variance term is through a scalar recursion that's referred to as state evolution, right? Because this is the way that we understand the performance of the algorithm as it iterates. So throughout, when I say state evolution, I'm just referring to kind of a recursive sequence that tells me something about the performance of the algorithm. Okay, so how do you actually use this AMP algorithm to provide some statistical analysis of the estimator itself. And the idea is the following, and this is, what was originally proved in Beati and Montanari's paper from 2011. So what they show is that with this AMP algorithm we just looked at, the AMP iterates converge in some sense to a fixed point. And the key property is that you can show that for any such fixed point, beta hat star is actually a lasso solution, right? So it actually minimizes the lasso cost function. So based on this sort of previous idea where, we can characterize the entries of beta hat at iteration k through, this simplified sort of signal viewed in Gaussian noise framework. What this means is, since beta hat star is a lasso solution, then we can characterize the lasso solution also using the state evolution equations. So what we'll see is that, everything we need to know about the lasso solution in an asymptotic sense in this large system limit can be precisely characterized through a fixed point of the state evolution recursion. So the recursion that tells us how the AMP algorithm is performing. So I'll just pause for a second to mention that, all of this is done in the regime where my measurement matrix X is IID Gaussian, right? So the main utility of AMP is not really as an efficient lasso computational algorithm, right? Because normally that's going to be a data matrix. So the IID Gaussian assumption is not a good one. But the point is that we're going to be using AMP rather as a device for gaining insight into the statistical properties of the estimator itself. And I will mention there are some problems where, AMP is used as an efficient algorithm, right? But these are generally in fields like compressed sensing or communications, where it's a designed matrix there, right? Where the IID Gaussian assumption is one that you can tolerate. Okay, so this is the main theorem that Beati and Montanari presented. So if we have beta hat L is indicating the lasso estimator for any strictly positive regularization parameter lambda, then we'll let sigma star and tau star be the unique solutions to these state evolution equations. And so these are just functions, again, of a random variable B, which has the same distribution as an element of my signal, and also a random variable Kasai, which is a standard Gaussian, right? So these are equations that one can solve. And so what the theory says is, then if we look at a pseudo Lipschitz loss function, which is a generalization of Lipschitz functions. If we look at a pseudo Lipschitz loss function acting on my signal, the true signal, and my lasso estimator, then we can characterize the asymptotic value of that loss using the state evolution equations, right? So in the convergence statement, right, the term on the right-hand side and the expectation is deterministic, right? This is a deterministic value that's given by this T star and the sigma star that are the fixed points of my state evolution equations. And so some examples of how this can be used, right, is by choosing specific pseudo Lipschitz loss functions. So the first thing you might think of is we can use this to evaluate the estimation risk, right? So the L2 norm between my lasso estimator and the signal itself, and this loss is completely determined by the state evolution fixed point. But you can also use these results to give you additional sort of fine-grained statistical analysis of the lasso estimator. So it can be used to evaluate, for example, the asymptotic sparsity of the estimator. You can also use this to evaluate like the type 1 or type 2 error of the lasso estimator, and so on. So by using different loss functions there, you can get kind of different statistical information about the lasso solution. Okay, so now what I'm going to do is I'm going to build on these results to show how this sort of the AMP theory for the Lasso solution can be used to tell us about something or tell us something about, multiple descent for minimum L1 interpolators for the linear model. Okay, so just some motivation for this problem, right? So, the conventional wisdom of statistics told us, we've probably all read the Elements book, right? But it suggests that too many covariants at training actually hurts generalization, right? But what we're seeing and kind of an evolving line of work coming from the ML community is that we're observing that overparameterization is in fact not necessarily harmful, right? And so this is generally, the double descent phenomenon that, Daniel and others have studied. And so a key kind of observation for explaining this phenomenon is that when, our models are trained on the training data using gradient type methods, many of the models converge to certain minimum norm interpolators. So it's, you're over parameterized. So there's tons of signal vectors that fit your model, but the one that the gradient methods seem to find is one that sort of minimizes some norm. And so therefore it's kind of implicitly favoring some lower complexity. So in particular, many algorithms favor a low L1 norm solution in this overparameterized regime. And this motivated Yuting Wei and her student Yue Li to sort of investigate statistical properties of this min L1 norm interpolator in order to study kind of trade-offs between overparameterization and generalization. And so the second example I'm going to look at is what AMP can tell us about, this min L1 norm interpolator. So, okay, so the idea is kind of the following, right? So when we're in this overparameterized regime where we have, P, our dimension is bigger than N, our number of samples, then if we look at a system like Y equals X beta, then there are going to be many vectors beta that interpolate the training data perfectly, right? So in particular, what we're going to study in this example, though, is one specific solution, which is the one that interpolates the data exactly, but minimizes the L1 norm. And so kind of the key the key step that relates it to the Lasso that we just looked at is to see that this is exactly just the Lasso problem, but we have to drive the regularization parameter lambda down to 0. Right? And so in this part of the work, Lee and Wei made a few additional assumptions. So in particular, they also assume that the noise is IID Gaussian and that the non-zeros and the vector beta have some known magnitude. And so the loss function we want to study, so the pseudo-Lipschitz loss that we're studying in this case is going to be the risk, right? Which is just the expected residual when we apply our estimator to a new data point. So the new data point is going to be independent of the estimator and independent of the training data and everything else. And so the theorem that Lee and Wei give us is kind of a description of this risk curve for these min L1 interpolators. And so all of this is based on AMP theory, which we'll see in the next slide. But the kind of summary that they provide is the following. So in this overparameterized regime, what they find is that there are two non-overlapping regions where the risk descends, is going down. And so then the sort of overall shape of the curve is determined by what the risk looks like in between these two descent regions. And it turns out that what happens in between those two descent regions depends on the sparsity level epsilon. So if the sparsity level is small, so if epsilon is small, so this is going to be like the red and green curves in the figure. The figure also I stole from Lee and Wei's paper. So for small sparsity, we see kind of a triple descent phenomenon. So, you have the initial descent in the underparameterized regime, then you have two descents in the overparameterized regime with a kind of increasing piece in the middle. On the other hand, if the sparsity is large, then the risk can decrease monotonically in this over-parameterized regime. They also show that asymptotically in the limit of this delta term, the risk is no better than the trivial estimator. So if you just estimated with the zero vector. Okay, so what I want to focus on, well, I think this result is interesting, right? Especially because it exhibits pretty different behavior than the L2, the min L2 interpolator, for example. But what I'd like to focus on is actually how we prove this. And what they did is they employed the Beati-Montanari analysis via AMP back from 2011. So kind of the first thing to notice is that when we're studying the asymptotic risk of this interpolator, it just boils down to studying the kind of L2 loss between the estimator and the vector itself. The tricky part, though, is that the original Beati and Montanari results were for fixed and strictly positive lambda. So what we need to do here is take the lambda to 0. So you kind of have to, do some extra work to get that to work out. So what Yuting and Yue did was, to accommodate this vanishing regularization, they constructed sort of a sequence of AMP algorithms that changed the parameters in sort of an epoch-based manner, and then they were able to analyze that sequence. And so there were some additional challenges here. So for example, as the lambda goes to 0, it's no longer the case that the cost function is going to be strongly convex around its solution. So you lose kind of some of the nice properties of the original problem. And so then you actually get these risk curves. So the risk curves that we saw on the previous slide come from analyzing the state evolution equations, right? So in particular, I think there were some challenges here for Yuting and Yue as well, because you actually need to analyze the fixed point of these state evolution equations, but with changing delta. And so, this was a little bit of a technical challenge. Okay, so before I give the general recipe for how to analyze statistical estimators with AMP, I just wanted to give one sort of theory application. And this is some result by Celentano, Montanari, and Wu that gives a lower bound on the estimation error of first order methods, and also shows that a form of AMP is optimal amongst the first order methods. Okay, so what do we mean by first order methods, right? Well, just some quick motivation, right? When we usually want to perform high dimensional estimation, what do? We construct some data dependent cost function that kind of encodes our views of the world, right? This encodes our modeling assumptions and so on. And then we minimize that cost with some fast algorithm. And the most popular algorithms for this task are first order algorithms, which basically just mean any algorithm that queries the cost by computing its gradient at a sequence of points, right? So these are things like gradient descent, projected gradient descent, mirror descent, accelerated gradient descent, and AMP, as it turns out, right? So the questions that Celentano, Montanari, and Wu wanted to answer are the following. So if we consider all the possible first order methods, what's the minimum statistical error, where I mean this L2 sort of risk again, that one can achieve? And so in which cases would these methods be suboptimal, and is there sort of, or what is the optimal trade-off between like the number of iterations and the estimation error? And so these are kind of the questions that this group set out to answer. And so what they're able to do is, using the AMP theory, they can develop precise average case lower bounds for such first order methods. In fact, for both convex and non-convex problems in a form of high dimensional regression. So for the rest of the talk, we're going to move away from the high dimensional or the linear regression model I introduced on the third slide or whatever, to look at a kind of more general linear model form. So now I'm just thinking that my output is some function of the linear measurements of my target of interest, and I know this function, right? So this encompasses things like phase retrieval, logistic regression, and so on. Okay, so in order to present their results, I need to define what I mean by these general first order methods. And basically, it's the following. A GFOM is going to be any algorithm that keeps two sequences of vectors that I've called U and V, where these vectors are updated by two operations. So one is just a row-wise application of some function, and then the other possible operation is multiplication by X or X transpose, where this is our sort of measurement matrix. So more formally, these are going to be all algorithms that are determined by sequences of Lipschitz functions that updates in the following sense. And again, what one can show, and what these folks did show, is that your usual sort of gradient descent algorithms for your standard problems like M estimation or Lasso or whatever fall into this framework. And so then the result is the following. So if beta hat k is kind of the output of any first order method, so any function of the following general form, then there's a lower bound on the estimation error of the output of the algorithm that's given by the MMSE function acting on the state evolution sort of equations of AMP. So the kind of idea, and this can be generalized to any sort of pseudo Lipschitz loss like we saw in the Lasso case, but we'll focus on estimation error here. And so the idea is, this says, okay, of any algorithm in this class, the AMP state evolution kind of determines this lower bound. And in fact, what they can show is that this lower bound is satisfied with equality by an AMP algorithm that uses kind of a Bayes update rule, right? And so kind of, the takeaway for this result, right, is that within the class of general first order methods, no algorithm can outperform Bayes AMP in terms of estimation error, right? And moreover, it's conjectured that in this problem, no polynomial time algorithm generally can outperform Bayes AMP. And so this is kind of the role that AMP plays in investigating these statistical computational gaps, because, we believe that in many problems of interest, AMP is the best possible computationally efficient algorithm. So if it fails, we believe all other algorithms will fail as well. I will mention that there are some problems where AMP does not seem to be optimal. But this is kind of an open area of research, looking at how to relate these usual techniques like the SQ algorithms, the sum of squares methods, and AMP, to see when they all perform the same and when they don't. But I'll just mention that the core proof strategy for this lower bound that Michael and Andrea establish is the following. So it uses this exact asymptotic analysis of AMP combined with a few technical observations, which are basically that any first order method in the form on the previous slide can be reduced to a certain AMP algorithm, right? And once it's reduced to that AMP algorithm, you can track its behavior exactly through the state evolution guarantees. And then the key point where, you get the inequality becomes an equality with Bayes AMP is that one can show that Bayes AMP is optimal amongst all the possible AMP iterations. Okay, so to wrap up in the last minute, I'll just give a general framework for using AMP to study statistical estimators. So this is kind of a framework that we put together that takes all of the known results, like the Lasso example in the beginning, and also the results on phase retrieval and M estimators and logistic regression and so on, and tries to write one recipe for using this proof strategy. And so this comes from the work with Oliver Fang, Ramji Venkataramanan, and Richard Samworth. So our goal was to provide, or one of the goals of the paper was to provide a program for systematically deriving exact expressions of the asymptotic risk for estimators that are constructed as solutions to a broad class of convex optimization problems. And so I'll just mention that I'm in this generalized linear model form where, my output is some function of linear measurements of a signal of interest. And so what we're going to consider is statistical estimators that are constructed as the minimizers of optimization problems of the following form. It's a sum of two terms. The first is a loss function acting on the output and the measurements of the beta vector, and the second is kind of a penalty function or regularization function, and we'll assume that both are convex. And so this form covers a pretty wide class of examples. So maximum likelihood estimators, maximum map estimators when beta is assumed IID. But also things like Lasso, M estimators, penalized logistic regression, and generalization. So while we're thinking of the penalty term here as being separable, with some slightly more sophisticated arguments, you can generalize to non-separable penalties and these sorts of things. And so the basic recipe is the following. It's easy to write down an AMP algorithm that has a fixed point that solves the optimization. So that algorithm is there in the paper. If you want to use the proof, you have to characterize the fixed point. You also need to verify the existence and uniqueness of the state evolution fixed point. So of the recursion that provides the performance guarantees for the AMP algorithm. And then you need to show that your AMP iterates converge to the fixed point in a suitable sense. And so I had this this note here that said that step 3 is actually the tricky part, because especially if the cost is not strongly convex around its solution, you need to prove that your cost being evaluated at 2 points implies that the 2 points themselves are close. But I gave this a similar talk to Yuting Wei, and she pointed out that for the min L1 interpolators, it's actually step 2 that is kind of the tricky part, because there you need to characterize this fixed point for all changing delta values. And so perhaps in modern problems, both steps 2 and 3 might be hard. And so just to wrap up, right, the outcome, if you can sort of fulfill this recipe, loosely speaking, what we get is a characterization of the asymptotic joint distribution of the estimator and the true signal under pseudo-Lipschitz loss. And so this takes on the form of that very first statement we looked at in the Lasso, but kind of non-rigorously, this is saying something about how beta hat and beta interact within pseudo-Lipschitz loss functions. But again, this class of loss functions is fairly general. It covers things like mean squared error, L1 loss. It also can tell us like asymptotic sparsity of the estimator, or you can use it to evaluate other performance metrics like type 1 or type 2 error. And in general, we expect that this recipe can be applied to a wider class of models than those that have been studied in the AMP literature to date. So we hope that, writing this all out kind of programmatically will be useful for, research in the future. And so just to summarize, I gave some examples about how AMP theory can be used to analyze statistical properties of estimators, specifically the Lasso and the min L1 interpolator in the case of high dimensional linear models. And then I showed a result that gives a lower bound on estimation error of general first order methods. And in fact shows that a Bayes AMP algorithm is optimal within this class. So AMP is kind of the best you can do. And then I proposed a general framework for characterizing high dimensional asymptotics of estimators when those estimators are constructed via convex optimization programs. And these are just the references for the 3 examples I gave. And so I will stop there. Thanks.
Okay, thanks, Cindy. Are there questions? Feel free to type in the chat or unmute yourself, just ask. But I can get started. So when in this example that you gave on how AMP can be used to study first order methods, somehow this seemed pretty exciting. Like this, somehow is it able to tell you what happens when you run AMP for, like polynomially many iterations or exponentially many iterations? Are there somehow can help tell the difference between what you can do within polynomial time and exponential time with these types of methods?
Oh yeah, that's a good it's a good point. So I mean, one of the things with AMP is you don't actually need that many iterations for it to converge in almost all problems. And so yeah, so I think you can get kind of precise sort of guarantees for the difference between if you run, K polynomial versus K exponential, but in practice, like if you look at the state evolution and its fixed point, it gets there pretty quickly. So, this is a little bit of a subtle point because, we have some finite sample. I have some finite sample guarantees actually for AMP as well that show that, in fact, if you have a fixed problem size and you start driving, the number of iterations too high, you kind of lose the concentration around the state evolution equations, in fact. So we're kind of lucky that in a sense, AMP doesn't need a ton of iterations to actually get to like convergence in most problems of interest. So
thanks. Are there other questions?
Actually, I do have a follow-up question to Daniel's question. I was wondering, yeah, this optimality thing statement sounded pretty nice. I was wondering how is there a general class of problems for which one can show this, or what's the most general class of problems for which it's known to be optimal among first order methods? And
yeah, so their result basically just says, it doesn't actually look at a specific cost function, right? It just analyzes. Well, it says that all of these first order methods that come in that form is essentially an AMP algorithm. So, if the kind of input you use in that algorithm is your Y, your observations, you know that the Bayes AMP is going to perform the best. And so, yeah, I mean, I'm not quite sure how to like, yeah, it's unclear to me if that gives a precise statement about the class of problems where AMP is optimal. Does that make sense? But the kind of the thinking is, we know in like low rank matrix estimation and this high dimensional linear regression that AMP does appear to perform or the same as the other kinds of like sum of squares, SQ, and these sorts of things. So we do believe it's optimal in those problems, but there's some examples like tensor PCA, for example, AMP no longer seems to be optimal. So perhaps when you go into different dimensions or something, it no longer is. So yeah, I don't think, honestly, perhaps Andrea has his head wrapped around which class of problems AMP is exactly optimal for, but I do not yet have that. So.
Okay.
Okay, thanks, Cindy, again. Great talk. Okay, so I guess we can move on to the next talk. Let me introduce the speaker. So the next speaker is Risi Kondor, who is a associate professor of computer science and statistics at University of Chicago, where he's been since 2011, I think. Before Chicago, he was a postdoc at Caltech and also the Gatsby unit in University College London. And he did his PhD in computer science here at Columbia in 2007. So Risi works on statistical machine learning and computational harmonic analysis, both theoretical foundations of these things, as well as applications to physics and biology. And today he's going to tell us about mathematical aspects of equivariant neural networks. Okay, take it away, Risi.
Thank you for that introduction. I just made my my presentation full screen. Can everybody see it all right? All right, good. Okay, thanks very much for the invitation. It's fun talking in a theory conference, especially talking about development in such an empirical field such as deep learning in a theory conference. So a little bit of a background. I started out as, at least at Columbia, I thought first that I was like an honest machine learning person, but then I kind of drifted towards these more mathematical and algebraic ideas and had a short run of publishing papers around that in the machine learning community. But eventually I started feeling that, these things are beautiful and they're powerful because they assume such a lot of structure, such specific and rigid structure in the data. And machine learning is not like that. So if I want to salvage my machine learning career, maybe I should forget about this algebraic stuff and work about more like statistical and fuzzier things. Now, the interesting thing is that then deep learning came around, which is the most empirical in some of all the recent branches of recent subfields of machine learning. And it turned out that the same ideas are just as relevant or maybe even more pressing in this realm. And in fact, there is a lot that purely algebraic ideas can contribute, it seems like, to the empirical performance of these neural nets as well. So it's a bit of a kind of circuitous story in that sense. Okay, so with that, my purpose in this talk is to just give you a sense of the general framework and these links between the underlying mathematics and the and practical neural networks. So to talk more about the general framework necessarily than about specific applications. Okay, so first of all, is what is equivariance? Well, equivariance is a very simple and general notion in mathematics. It relates to the fact when you have a map from one space to another, from V to omega, or V to W, and in addition, you have an action of something like a group on both of these spaces. So like the examples that will keep coming back to in the talk are rotations and permutations and other spatial symmetry groups, that sort of thing. Okay, so your data can be sort of shifted around in V and can be shifted around in W, and then there's also a map from V to W. Now this map is said to be equivariant to these actions if if it commutes with these two actions. So it doesn't matter if you first shift your object around in V and then you apply the map phi, or first you map the object to W with phi and then you apply, then you shift it around in the W space. So obviously this is a very general type of mathematical structure, and we are going to be, and this talk is going to be about how to enforce this sort of structure with respect to the action of specific groups and specific actions and specific maps in the context of neural networks. So as it turns out, this really does appear as a constraint in many domains that people are very interested in on the applied side of neural networks. The two which I want to highlight because is the two that we keep coming back to as well out of the pure scientific interest, as well as because of the mathematical side, are learning the structure or learning things about physical systems. I mean, physical systems that really live in three-dimensional space. A classical example is learning the forces between atoms, which you want to do, for example, when you want to do molecular dynamics, right? So molecular dynamics is about creating these movies of molecular systems or biological systems, usually at the levels of individual atoms, and you integrate in the forces between the atoms forward in time. In principle, of course, you could always derive the forces ab initio from something like Schrödinger's equation, but that's not what people do. It's not realistic. Instead, they use either some kind of some simplification, maybe a classical simplification or density functional theory, some sort of intermediate level of theory to capture these forces, because that's the only thing that's really realistic from the actual point of view of computational expense. So for a long time, these forces were the standard forces published in the literature, which like start out with some physical principles, but do have some elements of kind of empirical magic. These coefficients corresponding to particular types of real or fictitious interactions, and they've been tested in various settings. But it's clear that they have their limitations because of their simple functional form and their empirical nature. So the question is, now that we have so much data lying around, we can in principle simulate these small systems to our heart's content with, say, directly from quantum mechanics. Why don't we try and learn these forces? Okay, so this is a standard problem, and this clearly has significance in science. And it's clear that from the outset, it's going to have this equivariance property, because if you have the same physical system, but you rotate it, then, or a larger part of a system, or larger system, and part of it is just rotated with respect to the rest, then all the forces will need to rotate accordingly. So this is a case of equivariance with respect to SO3, the three-dimensional rotation group. Now, another context, which is interesting because it's entirely discrete, is the issue of permutation equivariance, so symmetric group equivariance in, say, graph neural networks. So there again, there's a hidden symmetry. The hidden symmetry is just the relabeling of the vertices of the graph. So it's a permutation of all the vertices. And if the graph happens to represent, say, a molecule, and you want to figure out its biological effects and so on, then obviously you don't want your algorithm to be sensitive to this ordering. So you want to be invariant to that, which means that internally in the neural network, you want to be equivariant to the action of the symmetric group. Okay, so for the purposes of this talk, I'm going to think of neural networks as just a sequence of interleaved linear and nonlinear operations. So there's the simplest possible kind of model of what a neural network is. It kind of conjures this idea of classical feed-forward neural networks, convolutional networks for image recognition, that sort of thing. So we're interested in how to make this sort of structure equivariant. The final goal being really to be equivariant, like in the force field learning case, or just to be invariant, like in the molecule learning case. But part of the story is that even if you want to be invariant at the end of the day, it makes a lot of sense, or to get a rich representation of your problem, you want to be equivariant internally. So if at the end of the day, you just want to be able to classify cats, we all know that this is one of the main driving forces behind machine learning, then you realize that you want to be invariant with respect to the rotations of the cats, but that does not mean that you first kind of canonicalize the cat right at the beginning, or every single layer you have these invariant layers with respect to the rotations of the cat. It makes often, or in general, it's better to have a network where internally you actually keep track of these transformations. So equivariant, and then you only symmetrize at the very end in the last few layers. Okay, so this is the contrast between invariance and equivariance, which fundamentally is a justification for why we are interested in the equivariant case. So at the kind of very pragmatic level, what we're interested in is what should our little neurons, like this guy in the middle, what should they do? So he receives input from other neurons, and each of them transform according to the group, because it just the group is still active, it's still doing something to these internal representations of the neural network. And then this little neuron does its thing. It applies the linear transformation and then the nonlinearity and spits out something. And the constraint is that what it spits out must also transform according to a specific predefined action of the group. So how do we ensure that if the inputs transform according to specified actions, then the output also transforms the same way? This is the crux of it. This is what the whole talk is really going to be about. And the main assumption that we make, or the starting point for our entire construction, is to assume that all of these actions are linear. It's very natural. It's like essentially every equivariant learning algorithm or neural network that I've seen starts out with this point. So it's very natural. It's also very helpful because it lands us in the realm of representation theory. Okay, so now we have a group and we have these linear actions of the group on something. So that means that this linear action is a representation. So the pedestrian way of representation is just a way of modeling the group with matrices. Okay, so it's a matrix valued function over some field F, such that the matrices that you associate the group elements multiply the same way as the group elements do. In a slightly more abstract way, you say that the representation is a homomorphism from the group to the general linear group over some space V. Okay, so this is a very well-studied branch of math because it turns out that it has a very rich theory and it has a huge breadth of applications, especially as we realize in the 20th century in modern physics. There are some extremely powerful with a wide-ranging theorems that kind of anchor it, as long as we make specific assumptions. And the specific assumption is come in two parts usually. One is that the group is compact, which means that it's finite or it's a compact Lie group. And two is that the space is a vector space over the complex numbers because it needs to be an algebraic completely closed field. So this is actually the context that we're going to be talking about. Okay, but the way to think of these representations, if you want to kind of think of something concrete, is really just a matrix valued function. Okay, so what are these key results from representation theory that we keep coming back to? It makes the whole mathematical theory so powerful and so relevant to actually building neural networks. The first one is this theorem of complete reducibility. Okay, so what does that mean? So first of all, you look at these matrix valued maps, these representations, and you quickly realize two things. One of them is that if you take one of these matrices and conjugate them by a constant matrix, then you get another representation. And that's not very interesting. It's essentially the same thing, just expressed in a different basis. Okay, so that's equivalent. So we don't need to talk too much about that. The other thing is that sometimes these representations can fall apart into smaller representations. And one way it can happen is that there might be just some subspace that is fixed by all these representation matrices of the group. Now, complete reducibility says that if this is the case, then actually these matrices then fully block diagonalize. So the orthogonal subspace is also fixed by all the representation matrices. Okay, so this is this is one of the reasons why it makes such a difference to stick to compact groups and stick to the complex numbers, because this is the sort of thing that kind of shockingly and suddenly breaks down when you go outside this sort of safe space. Having said that, if this complete reducibility holds, then it is a huge crush towards building up a very simple theory. In particular, it tells you that you keep doing this thing of taking your representations and reducing them into orthogonal parts and so on. And eventually you get parts which are not reducible anymore. So those are the irreducible representations. And when complete reducibility holds, that means that it basically tells you that everything else, all the rest of representation theory, is just built up from these irreducible, from the knowledge about these irreducible representations. So these are like the Lego bricks of representation theory, or like the primes of in number theory. So this is the context that we are going to be mostly focused on. And in particular, instead of always worrying about general representations, to figure out what really happens in terms of the neural networks, it's sufficient to express everything in terms of the irreducible representations and see like which parts of these internal activations, these internal messages, transform according to which irreducible representations. So a lot of representation theory is just focused about finding these irreducible representations, describing them for particular groups. And you can have a lot of fun just figuring this out for your favorite groups. So like if it's something very simple for the dihedral group, you see that you've got like 4 one-dimensional representations, and you've got 2 two-dimensional representations. Sorry, 1 two-dimensional representation. Okay, now another thing, I've already alluded to the rotation group, which is going to be important for them. So that's a totally classical subject. It even harks back to these 20th century ideas about solving partial differential equations and then the orbitals of the hydrogen atom and so on. So it turns out in that case that you've got a countable sequence of irreducible representations. They're indexed by an integer L, so it goes like L equals 0, 1, 2, and so on. The dimensionalities of these irreducible representations is always 2L plus 1, and it turns out that they're closely related to the spherical harmonics, maybe unsurprisingly. So there's a deep connection between these two. They are described by something, expressed by something called the Wigner D matrices, and there are closed form formulae for figuring them out. Okay, now another one, one of my favorite groups and favorite set of representations is the symmetric groups, the group of permutations. Now here come these weird Tetris shapes called the Young diagrams, the Young tableau. Okay, so it turns out in that case, if you're looking at the permutations of n objects, then in order to enumerate the irreducible representations, you need to enumerate the ways in which you can build these Tetris shapes, these Young diagrams consisting of n squares. The rule is that no row can be longer than the row above it. You figure out how many ways you can create these Young diagrams, and each diagram is going to have a corresponding irreducible representation. And it turns out that everything else about the irreducible representation is also harks back to these combinatorial objects and putting little numbers in them and so on and so on. Okay, so I'm just giving you this idea that this talking about these representations builds on very well established, very rich, but also still partially still quite active branches of mathematics called representation theory. Okay, now why did I subtitle the talk by saying that Shor's lemma is all you need? So Shor's lemma is something that comes up on like page 9 of a representation theory book, and it has a deceptively diminutive name and deceptively diminutive way of stating it in most books. So what Shor's lemma says is that if you have a linear map that maps from one space on which a group acts by an irreducible representation to another space in which it also acts according to an irreducible representation, then first of all, if the two representations are different, then this map just needs to be 0. So basically, if the map is to be equivariant and linear, then it needs to be 0. So If you break down everything into irreducible representations, and then you look at the equivariant maps, then Shor's lemma tells you that in order to be non-trivial, like needs to be mapped to like. So each irreducible representation needs to be mapped to part of the space which transforms according to the same irreducible representation. And moreover, if the two are the same irreducible representations, then this map can only be a multiple of the identity. So the fact that on these subspaces, these irreducible subspaces, the group acts in such a simple and, well, irreducible way, puts so much structure into the whole problem that your equivariant maps are very tightly constrained. This is the only thing that you can do. So this is what tells our little neuron what it is going to have to do in order to satisfy equivariance. So at least for the linear part of the operation, right? So it tells the neuron that, hey, you need to take all your input activations apart into their irreducible parts, kind of stack them up into these matrices, if you wish. And then in order for when you apply your linear transformation, in order to preserve equivariance, all that you can do is you can mix these different parts corresponding to the same irreducible representation with each other, but no messing around, like pushing information from one irreducible representation to another, and no like internally shuffling stuff within the same irreducible subspace. You're only allowed to have multiples of the identity map. So another way to say this is that what the linear transformation is going to look like if you take it apart in these matrices, which collect particular irreducible representations, is just going to be matrix multiplication from the right. So the columns get mixed together with each other, but you leave the rows alone. So this is something that we stated in a paper back in 2018, but it's really a direct consequence of Shor's lemma. And you see why this is of interest to building neural networks, because you start out with something fairly abstract. Like all of a sudden we're talking about these groups and continuous objects and all possible equivariance with respect to all possible transformations, and they're like difficult to describe, algebraic, blah, blah, blah. But it tells you that in order to ensure equivariance, all that you need to do, the actual operations of the neural network, are just going to be matrix multiplication. And PyTorch and TensorFlow and stuff are pretty good at matrix multiplication. Okay, so this is the story for the linear part. So and then the incoming activations are going to be the same era, get linear mixed together. So that's fine. This mixing is what you learn, what the neuron can learn. That's good. Now, what about the nonlinearity? So we need to have some nonlinearity, because otherwise the neural network is not really a neural network, it's just a linear map. But we need to ensure that the nonlinearity is going to be equivariant too. So how do we start that? Okay, so let's take a step back and let's think more generally about, for example, how do you get these equivariant parts, or these parts of the activations which transform according to particular irreducibles in the first place? Okay, so the answer is that, well, you do a non-commutative Fourier transform. So you write down the formula for the classical Fourier transform on the real line. You stare at it, and you discover that it's just an integral of your function with respect to a kernel, and that kernel happens to be an irreducible representation of the real line, of the real numbers, of the translation group, if you wish, on the real line. So why don't we generalize it and say that we declare that the Fourier transform on a non-commutative group, finite or infinite, is going to be the same. You just integrate the function x over the group. Here's the finite or discrete case that I wrote down, against each of the irreducible representations. And then each irreducible representation is going to give you a matrix, which is like the sum of these matrices, or the integral of these matrices as you integrate it over the group. And you're going to call that the Fourier transform of your function. Now, it turns out that this is not just a superficial analogy. This actually makes sense and establishes this very natural bridge between classical harmonic analysis and its non-commutative version, which satisfies all the basically versions of the same crucial theorems like translation theorem, convolution theorem, blah, 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 that we're used to from classical harmonic analysis and signal processing. At the same time, especially for the more mathematically minded, it's kind of interesting that when you normally think of Fourier transform, you think about Fourier transform from a function on the real line to a function on the real line, or from the cyclic group of size n to essentially the cyclic group of n elements as well. So there's a duality there, right? You start out with something on the real line and you end up with something on the real line. Where here it's broken. You start out with something on a group and you end up with a bunch of matrices. So that's a bit disconcerting at first, and then you can start thinking about, okay, so but then how do I even define the notion of, say, multiplication in the space of these matrices? What does that mean? And then what happened to the duality? Turns out that there's a much deeper notion of duality, but it requires a significantly more abstract way of looking at the whole problem to figure out this duality between the group itself and the systems of irreducible representations, as when you're on the non-commutative case. Anyway, so in other respects, this Fourier transform is very well behaved. So what I was saying is that if you look at the convolution theorem, for example, it's a direct analog in the non-commutative case. The only thing that changes is now that you're multiplying matrices together. So for the convolution on the group becomes matrix multiplication in the space of matrices in Fourier space. Equivariance, I mean, if equivariance is the action of the group, the action of the group on functions on the group is just translation on the group, and that just corresponds to multiplying these Fourier matrices by the corresponding representation matrix. So that's what you see here on the bottom. Okay, so so there is this nice theory of non-commutative harmonic analysis, and actually this is how you generate the equivariant parts that go into that your neural network, your little neurons can then correctly deal with in the first place. Moreover, if there's a Fourier transform, and if there's a nice algorithm for computing the forward and the backward transform, which there is. There's a whole separate literature on these non-commutative Fourier transforms and making them efficient, similarly to the classical FFT. Then one way you could create a nonlinearity is to say that, okay, and whenever I need a nonlinearity, I'm going to go back onto the group itself. So in the case of learning something that's, say, rotation equivariant, I'm going to express it on the rotation group, or I'm going to express it on the sphere, and then apply a nonlinear kind of function pointwise on the rotation group or on the sphere. And then I need to go back into Fourier space again in order to do this linear transformation, which it boils down to matrix multiplication again. So that's certainly an option, and that's the part taken in some papers, for example, in some of the spherical CNN papers. But another option, which seems potentially much more attractive, is to try and do the nonlinearity in Fourier space as well. Okay, so this is what I want to talk about in the next 10 minutes. So what operation can we do? We've seen how we can do linear operations in Fourier space, which are equivariants, but what can we do in Fourier space which is nonlinear but is still equivariant? And basically, there's one type of operation known to humanity which you can do and get away with this, and that's to take tensor products. The reason for it is because if you take two representations and take the tensor product, then you get another representation. This is very easy to see, and because of complete reducibility, that representation must again be reducible into irreducible parts. So this actual transformation, which does this for you, is called the Clebsch-Gordon transformation. And it's again one of these major points of obsessions of mathematicians in representation theory, because it's not at all, in the general, it's not at all trivial to derive for any group that you might dream up. But of course, for something like the rotation group, it's a really canonical, well-known mathematical tool. It's very familiar to physicists because I mean, because its interpretation is so natural too. So of course it comes up in say physics problem. If you in quantum mechanics, you take two systems and they both have spin or angular momentum, that means that there is something in the wave functions, transform according to irreducible representations of SO3, and then you combine the system. That means that you take the tensor product of the wave functions. And then you ask yourself, okay, so now what is the total spin or the total spin angular momentum? So to answer this question, you need to apply exactly this transform. So this is a very canonical type of operation that crops up when you actually put representation theory to use. And again, it's a linear transformation with a fixed unitary matrix, which just does this decomposition into irreducibles. Maybe the matrices in the middle get a little large because of the tensor product, but still, I mean, after all, it's just a linear transformation. Okay, so then it's very easy to turn this into our equivariant nonlinearity. We just say that we've got these two activations which transform according to known irreps. We take the tensor product that's not going to transform according to one of these irreps again, but then we apply the Clebsch-Gordan transform, and we're back into the safe land of everything being decomposed in terms of the irreps. And hey, it's not linear, right? It's a tensor product, so there is a product there. So we tried out this strategy in a series of papers. It also crops up in other works in the literature. And it's not so surprising that it crops up because the tensor product crops up in physics all the time, because it's it corresponds to very natural kind of physical types of interactions between stuff. So just intuitively, without necessarily all the representation theory of baggage, it was proposed in this context of learning the behavior of physical systems, but it nicely falls in this general theory. And it does have the advantage that even if you build a neural network with not necessarily directly trying to model physical interactions, the kind of interactions that come out, this kind of sequence, like this iterative Clebsch-Gordan products, if you unwrap it and write it down in one formula, it's kind of starts looking like an actual physical law, the types of interactions that people are used to in physics and can interpret. Now, on the downside, you can say that, hey, this is not like a proper neural network anymore, right? Like normal people don't use quadratics as nonlinearities in their neural networks. They have a bad reputation for being hard to train, which might or might not be true, and depending on the context. And also, it does not necessarily mesh with the people's idea of what the nonlinearity is for. So if you're building a neural network for recognizing images, then the nonlinearity, part of the interpretation is that, hey, it's kind of a pattern matching thing, right? You have these convolutions and you want to know whether the pattern matched or not. So you want to have something very drastic that is close to just a Heaviside function or a ReLU or something like that, with saying that either you've matched this thing or you have not. Whereas a quadratic is this kind of fuzzy, elusive thing. On the other hand, it's nice. There's no fact that it's nice and smooth. Is again when you're actually trying to learn physics. I mean, the classical physical interactions are also nice and smooth. So that's what potentially in your favor. It's just a different approach. It just depends on the particular case whether what the implications of using these Fourier space tensor product nonlinearities are. Okay, so and anyway, we've got a proposal for what our neuron should do. It should first do this linear operation involving mixing the different irreducible parts of the activation for the with learnable weights, and then it applies a Clebsch-Gordan transform or iterative Clebsch-Gordan transforms. And actually, this whole idea now has a whole plethora of different applications in different fields and different variants on this idea. Somebody has put together an awesome list of all the awesome equivariant neural network papers, and it keeps growing. So this is way out of date already. There are dozens or maybe hundreds of papers on the underlying theory, on the relationship of the math, on permutation equivariance and its application specifically to these physics problems and the graph learning problems. Okay, I need to be a little bit mindful of time, so I need to choose what I want to talk about. Maybe I'll talk for a couple of minutes about quickly go through this section on the relationship to convolution, because Fourier analysis is always about looking at two things from the same thing from two sides, from the real space picture and the Fourier space picture. And I've already closely hinted that one of the attractions of these Fourier space neural nets is that what looks like matrix multiplication in Fourier space is really convolution in the real space. So is there a natural connection? So does this mean that there's a connection to classical convolutional neural nets? Of course it does. So the classical convolutional neural net implements as the linear transformation just the ordinary convolution operation, which you can write down like this, but you can also just think of it very explicitly as pattern matching, right? So you take the correlation, which is closely related to convolution, between your pattern and then the part of the image. Usually the filters are small, so these are small patterns, and that gives you the activation of the next layer. And then you do the same kind of pattern matching at the next level, and so on and so on. So this does multiple things for you. First of all, intuitively, or just from like staring at this format, you see obviously clear that this is going to be equivariant with respect to translations of the plane. But it also does another thing for you, and that is it builds up this kind of hierarchy of filters, right? Because one filter detects something in the image, and the next filter detects patterns in the detected patterns, and the patterns in the detected patterns, and so on and so on. So there's also this kind of hierarchy in terms of the semantics of the neural net going on, or of the individual layers. And finally, there's also a sense in which you are capturing information at different scales. As you go higher up in the neural network, you're going to be the neural nets on the individual neurons are responsible for larger and larger areas in the original domain. So they capture information at higher scales. So this is wonderfully borne out by training up these neural nets and then looking inside. So these are some classical figures that I stole from a paper by Zeder and Fergus back in 2013, where they trained on ImageNet, and then they looked at the individual neurons, what the filters that they learned, and in particular, which parts of the original images those filters were the most sensitive to. And what you see is also gets the neuroscientists excited, because it has almost like a biological interpretation potential as well. You realize that these filters at the first few levels just pick up very simple things like little ridges or gradients. In the next level, they pick up something which is like a slightly more complicated, but still kind of subtle local features, like little circular parts, or little straights, or tiny bits of patterns. And hey, layer 4, all of a sudden you've got like these dog face detectors. Okay, so this is pretty striking, and certainly a good good justification for this kind of semantic hierarchy idea. So this is the at the end of the day, however, everything just falls out of this convolution operation, which is the classical translation equivariant linear operation in these neural networks. Slight variation on this is steerability, where you also allow for rotations. So that's an interesting twist, but we don't really have time to talk about it. Now, as I said, there is a clear analog of the notion of convolution on groups. And also there's a clear analog of the Fourier of the convolution theorem as well. Okay, so in particular, let me just skip this. So in particular, the convolution theorem boils down to matrix multiplication. So saying that the neural network will, at the linear operation, has to do convolutions is actually exactly the same as we had the theorem about a couple of slides back, saying that the linear transformation in the neural network needs to be matrix multiplication of particularly reducible parts. Okay, so this one illustration of this was this series of works by Cohen and first, and then we also had a paper on spherical CNNs. Okay, so that's like that's in some ways like the simplest possible deviation or simplest excursion from the land of a commutative equivariance to commutative group to something that's non-commutative. Okay, so that's clear. What the interpretation, what you want to do is fairly clear. You've got a big image painted on the sphere, and then you want to recognize what's on that image with the same, so with some kind of generalization of the classical convolution or neural net idea. So intuitively, what you want to do is you want to have these filters that you match against parts of the image on the sphere, and then they match with some to some extent when it gives you it gives you a scalar, which is again can be regarded as a scalar valued function on the sphere or a scalar valued function on the rotation group, and then you want to build up a hierarchy out of this. So you can write down what the convolution on the sphere is, and you can do this operation, but actually trying to do convolution on the sphere in real space is very painful. You realize that it's much easier if you express everything in sort of spherical harmonics. But there's this simple formula for convolution in terms of spherical harmonics. And then you realize that actually what you're doing is the sort of Fourier space Fourier neural network that I talked about in the first part of the talk. So in fact, the different sets of spherical harmonic coefficients correspond to the different irreducible representations of the rotation group and so on and so on. So these filters really just correspond to these types of linear transformations, matrix multiplication of these irreducible parts from the right that we talked about before. So there's this perfect correspondence between the real space picture and the Fourier space picture. And in fact, you can write down a general theorem which says that if you have an equivariant, if a neural network which is equivariant to the action of the group, and you express everything in terms of functions on the group or functions on spaces on that the group is acting on, called homogeneous space on the group, then the only equivariant linear operation that you can have is this generalized form of convolution. And so the classical convolutional neural net is just a special case. And furthermore, in Fourier space, this corresponds to matrix multiplication. Interestingly, it seems like it turns out that the structure of these matrices also has a very clear interpretation. So when you write down the Fourier transform of a function, of a generic function on the full group, then these are full rank, like dense matrices. On the other hand, when you say on the sphere, then you really only have a spherical harmonics which correspond to just the single column of these matrices. And there are these intermediate cases as well. So it turns out that the structure of the matrices corresponds to which homogeneous space of the symmetry group your data lives on. So by designing these weight matrices to have specific sparse row and column sparsity patterns, you're actually making kind of a group theoretic constraint by saying determining which homogeneous spaces of the group the specific activations need to correspond to. Okay, so we don't need to go into this is just a couple of slides showing the nasty details for the case of the rotation group. And I also had a section on how we put this to use for learning these physical interactions, discussing the fact that like the analogy with the shape of classical interactions, if you write down the actual way that monopoles and dipoles and quadrupoles interact with each other, you see that it is similar to, it actually involves the same kind of products. Okay, so I guess it's time to wrap up. There are a couple of thoughts to conclude with. One of them is that there's a lot of fascinating theoretical work still to be done in this space. At the same time, I really want to see these mathematically motivated equivariant neural networks to be used in practice. And I realized that the fact that it starts out with having to have some understanding of representation theory, and particularly the hard constraints that inputs on the architectures can be a barrier to them being implemented. Also, the sheer fact that there are these operations, so PyTorch and TensorFlow are really good at tensor products and ReLUs and so on, but there's no Clebsch-Gordon transform there, and there's also no FFTs. And these are algorithms which are very they're mathematically very well defined and they're fascinating to work on, but they're also easy to mess up. And if you mess it up, then your equivariance is gone and something strange is going to happen in a neural network. So there's I think there's a good case for building software that actually has these operations baked in, like classes which correspond to quantities transforming to particular representations of particular groups, and which guarantee that the operations on them guarantee that they're going to keep their mathematical properties. They're going to behave the right way with respect to the action of the group. So we're actually putting quite a lot of work into implementing such a system, which makes the whole thing easier to use. There's also some interesting the details, kind of computational details on how these irreducible representations, even in the case of SO3, interact. And I can skip that, but that's further reason to think about another entirely slightly more sophisticated implementation. And now I wanted to also make a relation to, or to talk about the relationship to graph neural networks, which I said need are like a version of this, involve a version of this idea related to the symmetric group rather than the rotation group. So that's that's the object example in the discrete case, but obviously don't have time for that. So all that I can do is to show you my pretty slides without the commentary. We put this to use in actually building a neural network for molecules that is specifically sensitive to individual functional groups. So that's one of the newest works from my group driven by Eric Tida, who's actually a chemist by training, but has diverged in towards the machine learning direction. Okay, I want to wrap up by just listing a couple of directions in which I think this game could go or should go. So first of all, I only talked about equivariance to groups, but this kind of setup appears in a slightly more subtle form when you are not working actually on a group or on a homogeneous space of a group. You're just working on a manifold, and the group is the internal symmetry of the manifold. So this is the case of geometric deep learning or building neural networks on Riemannian manifolds, where the invariance is not with respect to the global transformations of the object itself, but it's the invariance with respect to how to put the charts on the manifold. So this leads to something called gauge equivariant CNNs, pioneered by Taco Cohen and Max Welling and a couple of other people, which in some form is the most general embodiment of all of these set of ideas. I mentioned steerability, which is a twist on the classical convolution idea, where not only in the case of image recognition, you have essentially a field of activations, which is not just invariant with respect to translations, but also internally has a kind of rotational degree of freedom as well. And the whole thing is invariant with both translations and rotations. Okay. Now, in the part that I did not get to with graph CNNs, there are a host of really interesting theoretical questions about the expressive power of these different architectures and how it matches up with the group theory. Equivariant generative models are a wide open field. So how do you combine this? Like, how do you build a neural network which can really generate the same molecules for you, which is equivariant to the permutations, but provides non-trivial answers? The interesting questions to exchangeability in statistics and so on. The multi-scale stuff. So I advertise the fact that classical CNNs are wonderful because they automatically learn this multi-scale representation of data. On the other hand, this is something that's not really easy to do in Fourier space. So the spherical CNN throws that aspect out the window, for example. How can you marry the two? How do you know, in Euclidean space, you have a grid where your image lives on. That's something that's really easy to coarsen at to begin with. But if you are on the sphere, then putting a regular grid on the sphere is already not possible. And then how you figure out the notion of coarsening or discretization there, that's not at all simple. And then there's a host of really tantalizing applications in physics, and like I mean real physics. So learning wave functions of various of these kind of physical model physics systems, the Ising model, the Heisenberg model, and the host of others, the hard quantum systems. How you implement these symmetries there, and what it buys you. We just came out a paper addressing something called the J1, J2 Heisenberg model with a neural network, which actually both embodies both permutation and SU2 symmetry, and uses the Shor-Val duality, and maybe not entirely in a trivial way. And when we're talking about this sort of thing, there's also a natural connection to quantum computing, because in some of these transformations, they turn out to be exactly the same transformations that come naturally in quantum mechanics, that quantum computers can have a huge edge in over classical computers. So potentially this even defines new complexity classes for quantum information theory. Okay, thanks very much.
Thanks, Risi. Yeah, I don't know if anyone has any questions for Risi. That I can add a quick question, which is, I guess you were, in this final slide, you were listing some kind of open problems. Are there open problems related to, more classical theory of neural networks, such as like universal approximation or optimization, things of this sort?
Yes, I think so. The different ways of phrasing it. One of them is that if you have one of these equivariant, like if you do not have equivariance, there are these classical universality results. What are their analogs when you for these equivariant neural networks? Sure. If you phrase it very simply, like if you just say, okay, now I have a neural network which is the most general possible, but it is equivariant to this group, then maybe the results are not going to be, maybe the results are going to be fairly straightforward, because the analog is going to be, if you have a universal approximation in the original domain for the non-equivariant stuff, then with the equivariant neural network, you get universal approximation for with the equivariance constraint. But there are other questions which do not, which are more subtle, maybe do not have a direct classical analog, such as like, can you, with a particular architecture, can you uniquely represent given inputs, right? So that's not even necessarily in terms of neural nets and training them, but if at the end of the day, for example, you have these equivariant layers which finally build up something invariant, then in the process, then do you lose any information beyond the kind of modding out by the action of the group? And so this makes it sound almost like a question from classical invariant theory. So even predating, even outside the neural net era, this is pretty crucial. In graph and neural nets, for example, or the application of these ideas in general, these equivariant ideas to graphs, this is kind of important, right? Because you can use these harmonic analysis ideas to cook up graph invariants. And they look like fundamentally different to the classic, to these combinatorial invariants. And then the question is just how powerful are they? Like, what kinds of graphs can they distinguish between? And do they have any bearing on the graph isomorphism problem?
Hey Rishi, how are you?
Hi.
Thanks for the talk. I guess two kind of very related questions. So one, I think probably like, I guess I know that the answer is going to be no, but nevertheless, I'm kind of like an outsider to this area. So I guess somehow like the idea with all of these kind of equivariance-based networks is kind of inductive bias. So you would hope for some kind of like, sample complexity separation to say like, for task, like, such and such or something. Like if you train this kind of architecture, you need a smaller sample complexity than if you, let's say, train a fully connected network.
Right.
So I suppose even for just kind of fully connected networks, we kind of have pathetically little, I guess, like proper separations between the, sample complexity of, let's say, like you train like a gradient descent based algorithm with a fully connected network and with like a convolutional network, and then you can cook up some data distribution such that the sample complexity is like better, let's say. Do we have anything of this type for like either graph neural nets or like equivariant nets, like really any of these sort of inductive bias based kind of like built-in inductive bias types of architectures?
It's not what I'm most familiar with, so I want to make sure that I don't disregard some work that might have recently come out, which is very powerful in this regard. For graph neural networks, there are, I think, some interesting results and on the significance of invariance and particular different types of in particular comparing not in terms of just sample complexity, but comparing it to like the Weisfeld and Lehmann hierarchy, that sort of thing. Mm-hmm. But more generally, if all that you have is this equivariance constraint, then that itself is not going to be is not going to change the in terms of inductive bias and sample complexity and approximation error does not fundamentally change the picture. So that does not buy you a lot. And I mean, it is a bit like modding the space out with the action of the group. So now you're in a smaller hypothesis space, good. But if you formulate the problem in this abstract way that learning theorists like to form it, when you've got a space and where you're learning a space of functions on the space, a hypothesis space, and you're finding one, blah 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 blah, then sure, the space gets smaller, but it gets smaller in this fairly simplistic way, which if you were not happy with your bounds at the begin with, and then after modding out with a group, you're not going to be happier with it afterwards.
Okay, so I guess like yeah, I mean, I think that like the other question is kind of also, I guess, related to this, which is that sort of I mean, it's sort of alternative to these kind of cooking up your inductive bias into the architectures to cook up augmentations, right? Like the alternative is basically you take your data and you just randomly sample some group actions or something. And so like, is there kind of convincing cases where I guess like one approach dominates the other or vice versa?
Right. Okay. This is my favorite question. Maybe I should. So,
I'm not a plant, I promise.
Right. So, sure, in some cases you can get away with data augmentation. If what you're really interested in is finding cats in YouTube videos, then maybe you don't need this stuff because there's so many YouTube videos to begin with. And anyway, it's like upside down cats are less common and so on and so on. Okay. But in a slightly different realm, in a more challenging or more interesting scenario, first of all, I am kind of a believer that if you know something, then just because you're doing deep learning, you don't need to forget it, and you might as well try and use it, right? The other part of it is that there are situations where you actually want to be exactly equivariant or exactly invariant. So if you are doing learning from graphs, and it turns out that you're doing great on the standard data set, but really the reason you're doing great on the standard data set is because it comes from some chemistry domain, and there's a conventional way of ordering the atoms, and nobody has remembered to randomize over that. So you're actually picking up some some hidden information in the data that was put in there by the way that the stuff is listed in the order and the rows and the columns of the matrices. Then maybe you're not really doing graph learning at all, right? You're reverse engineering a particular data set. And if for molecular dynamics, if you learn a force field, but it's not equivariant to rotations, then that means that you put it into the molecular dynamics engine, and then everything is going to be messed up. So you run your trajectories, and the angular momentum is not conserved, and conserved, energy is not conserved, and you discover that depends on how you represent your, I don't know, your cell and the receptor on it and the ligand. Either you're going to, the same drug is going to look like it has a totally different effects. So that's not really what we want to do in science.
Cool. Thanks so much.
Okay, thanks so much. All right, I think we'll end the session here, and then thanks again.
All right, thanks very much.
I guess for people remaining,